Right now, every black hole in the observable universe may be hiding something. Not matter, not light, not time. A door. The same equations that proved black holes existed, equations tested to 12 decimal places, equations that predicted the exact shape of what we photographed in 2019. Those same equations contain a second object, a mirror, a region of space-time where the rules run backwards, where nothing can enter but everything inside must eventually come out. Physicists call it a white hole. They have never found one, not once, not anywhere. Yet the mathematics insists it must exist. And in 2025, something extraordinary happened. A new quantum theory proposed that every black hole, every single one, is already becoming its opposite, from the inside, at a level beneath space and time itself. What does that mean? We are about to find out. A small team worked hard to make sure every fact in this video was verified and every idea was worth your time. A like tells them it was. In 3, 2, 1, liftoff. There is a photograph sitting in the archives of the Event Horizon Telescope collaboration that should not exist. Not because it is faked, not because it is in dispute, because for most of the 20th century, the majority of physicists believed it could never be taken. The image shows a ring of fire, a glowing orange halo of superheated plasma, warped into a perfect circle by the most extreme gravitational field in the known universe, surrounding a central darkness so absolute that light itself cannot escape it. That darkness is not an absence of data. It is not a gap in the telescope's sensitivity. It is a confirmed region of space-time from which nothing, no matter, no radiation, no signal of any kind has ever emerged. That photograph was released on the 10th of April, 2019. The object it depicts sits at the center of a galaxy called Messier 87, approximately 55 million light-years from Earth. The mass of that object is 6.5 billion times the mass of our Sun. Every second of every day, material falls across its boundary and vanishes from the observable universe forever. That boundary has a name. It is the event horizon, and the object behind it is a black hole. 3 years later, in 2022, the same collaboration turned its instruments toward the center of our own galaxy and produced a second image. This one was harder. The Milky Way's center is a chaos of gas and dust and swirling stellar populations, and the black hole at its heart is more active, its environment more turbulent, its accretion more variable. But the result was the same. Another ring, another darkness. This one, smaller in apparent size, located roughly 26,000 light-years from Earth, and confirmed to have a mass of approximately 4 million times the mass of our Sun. Its name is Sagittarius, A star. It has been sitting at the center of our galaxy for the entirety of Earth's existence, for the entirety of life's existence on this planet, for the entirety of the solar system's 4.5 billion year history. It was there before the first dinosaur drew breath. It will be there long after the last star in the Milky Way goes dark. These are not theoretical constructs. These are not mathematical predictions awaiting verification. These are photographs. These are measured masses. These are objects that warp the paths of stars around them in patterns that can be tracked in real time by orbital telescopes. For over 2 decades, the European Southern Observatory's gravity collaboration tracked the orbits of stars near the center of our galaxy, stars moving at velocities of thousands of kilometers per second, completing full orbits in periods as short as 16 years, orbits that only make sense in the presence of an invisible, compact object 4 million times more massive than the Sun. The data is not ambiguous. The conclusion is not contested. Black holes exist. They are the most extreme confirmed objects in the physical universe, and they are not rare. Astronomers estimate the observable universe contains somewhere in the range of 100 billion trillion black holes. The number is almost certainly an underestimate. Almost every galaxy we have ever observed contains a supermassive black hole at its center. The Milky Way has one, Andromeda has one. Every elliptical giant, every spiral, every active galactic nucleus in the sky, there is a black hole inside it. They are as fundamental to cosmic structure as stars. And before this episode is done, that fact is going to matter in ways that should make you deeply uncomfortable. But to understand why, you need to understand what a black hole actually is. Not the pop science version, not the visual shorthand of a drain pulling water into a spiral. The real thing, because the real thing is stranger, more precise, and more philosophically unsettling than almost any description of it that has ever made it into a classroom or a documentary or a headline. And the real thing, precisely because it is what it is, turns out to contain a secret that the equations have been keeping since 1915. Everything begins with gravity. You already know gravity. You know it as the force that pulls you toward the Earth's surface, the force that keeps the moon in orbit, the force that drew the planets together from a disk of gas and dust 4.5 billion years ago. For most of human history, gravity was described by Isaac Newton's equations, a force of attraction between any two objects with mass, proportional to the product of their masses, and inversely proportional to the square of the distance between them. Those equations are extraordinarily good. They predict the orbits of the planets to many decimal places. They sent Apollo astronauts to the moon and back. They are right enough to be useful for almost every engineering application humans have ever attempted. But they are wrong. Not dramatically wrong. Not wrong in ways that matter at everyday scales and speeds. But wrong in a way that becomes catastrophically apparent when you push to extremes, when masses become enormous, when speeds approach the speed of light, when the geometry of space and time themselves begin to bend. In those regimes, Newton's gravity fails, and the theory that replaces it changes everything about what we think space, time, and gravity even are. In 1915, Albert Einstein completed the general theory of relativity. It took him 10 years of work. The core insight is deceptively simple to state and almost impossible to fully internalize. Gravity is not a force. It is a curvature of space-time. Mass does not pull other mass toward it through some invisible action at a distance. Instead, mass and energy curve the fabric of space-time, and other objects follow the curves. They roll along the geometry of space-time the way a marble rolls along a curved surface. What we experience as the force of gravity is actually the geometry of the universe telling us where to go. This reframing is not merely philosophical, it is mathematically specific. Einstein encoded this idea in a set of equations, the Einstein field equations, that describe precisely how the distribution of mass and energy in a region of space-time determines that region's geometry. They are among the most beautiful and among the most difficult equations in physics. They are also among the most dangerous, because when you apply them to extreme situations, a star collapsing under its own gravity, a mass concentrated into a sufficiently small volume, they predict something that sounds like it should be impossible. In 1916, Less than 2 months after Einstein published the general theory of relativity, a German physicist and astronomer named Karl Schwarzschild was serving on the Russian front of the First World War. He was dying of a disease contracted in the field. And in the middle of all of that, the artillery and the mud and the illness, he solved the Einstein field equations exactly for the case of a perfectly spherically symmetric, non-rotating mass. He produced the Schwarzschild solution, the first exact solution to Einstein's equations, describing the geometry of space-time around a compact spherical mass. The solution is strange in a way that Schwarzschild himself may not have fully appreciated. At a certain distance from the mass, a distance that depends entirely on how much mass is present, the equations produce a singularity. Not a singularity in the sense of a mathematical technicality that can be cleaned up with a change of variables. A singularity in the sense of a surface in space-time where the causal structure of the universe fundamentally changes. Schwarzschild calculated the radius of this surface. It is now called the Schwarzschild radius. For an object with the mass of our Sun, the Schwarzschild radius is approximately 3 kilometers. For an object with the mass of our Earth, it is approximately 9 millimeters. These numbers mean the following. If you could compress the entire mass of the Sun into a sphere with a radius of 3 kilometers, and if you could compress the entire mass of the Earth into a sphere smaller than a marble, the geometry of space-time around those objects would develop a feature from which nothing can escape. That feature is the event horizon. The event horizon is not a physical surface. There is no wall. There is no membrane. There is no material object sitting at the boundary. It is a geometric property of space-time, a location defined by the curvature of space-time, becoming so extreme that the escape velocity equals the speed of light. For any object inside the event horizon, every possible path through space-time, every trajectory, every direction, every course correction leads inward. This is not a statement about technology. It is not a statement about how fast you could theoretically travel. It is a statement about the geometry of space-time itself. Inside the event horizon, the direction toward the singularity is not a direction in space. It is the direction of the future. You cannot avoid falling toward the center for the same reason you cannot avoid moving toward tomorrow. Think about that carefully. When you are outside a black hole, you have 3 dimensions of space in which you can move freely, and 1 dimension of time that flows relentlessly forward regardless of what you do. You cannot travel backward in time. You can only move forward through it. Inside a black hole's event horizon, something similar happens to one of the spatial dimensions. The dimension pointing toward the singularity becomes the future. You cannot choose not to fall toward the center any more than you can choose not to age. The geometry of space-time has hijacked one of your spatial degrees of freedom and converted it into an inescapable temporal direction. There is no way out. Not for matter, not for radiation, not for light, not for information. This is what black holes are. Not dramatic vacuum cleaners pulling matter across the universe. Not cosmic drains waiting to swallow the galaxy. Extreme regions of space-time curvature in which the geometry itself has been so severely deformed that causality, the structure of what can influence what points, only one direction. Inward, always inward, forever inward. Now add one more element, the singularity. At the center of the Schwarzschild solution, at the center of every non-rotating black hole, the equations predict a point where the space-time curvature becomes infinite. A point where the tidal gravitational forces grow without bound. A point where the density of matter becomes, mathematically speaking, infinite. Physicists call this a singularity, and it is, in a very precise sense, the place where the known laws of physics stop working. General relativity cannot describe what happens at the singularity because the equations return answers that are physically meaningless, infinite quantities, undefined terms, broken mathematics. The singularity is not a prediction of what the universe does there. It is a signal that the theory has been pushed past its domain of validity. Something else must be happening at the center of a black hole, something that general relativity is not equipped to describe, something that requires a deeper framework of physics. What that framework is and what it predicts for the center of a black hole is precisely the thing that turns out to have everything to do with white holes. But before we get there, we need to establish just how certain we are that black holes are real because the certainty matters. It matters because the same equations that gave us black holes give us something else, something that nobody has ever observed. And if those equations were right about black holes, if they predicted something that seemed impossible and turned out to be real, then we have to take very seriously what else they are predicting. The observational case for black holes is not built on a single line of evidence. It is built on many independent lines of evidence, each one arriving from a completely different method of measurement, and all of them agreeing. Begin with stellar mass black holes. These are black holes formed when massive stars, at least several times more massive than our Sun, reach the end of their nuclear fuel supply and collapse. The collapse is catastrophic. In fractions of a second, the core of the star implodes. If the mass is sufficient, it forms a black hole. The outer layers of the star are expelled in a supernova explosion visible across cosmic distances. The black hole left behind has a mass typically between about 5 and several tens of solar masses. We know these objects exist because we observe them in binary star systems, systems where a black hole orbits a normal companion star. Material from the companion is drawn toward the black hole, forming an accretion disk of superheated gas that radiates intensely in X-ray wavelengths. We have observed hundreds of these systems. The orbital dynamics are precisely consistent with compact objects of the right masses. No other known physical object could produce the observed X-ray luminosities and variability patterns. These are black holes. The evidence is conclusive. Then there are supermassive black holes. These are the giant objects with masses ranging from hundreds of thousands to tens of billions of solar masses, and they sit at the centers of almost every large galaxy. The evidence for them is equally solid. At the center of our galaxy, the stellar orbits tracked by the gravity collaboration trace out ellipses that, when analyzed using Kepler's laws, the same laws that govern planetary motion in our solar system, require a central mass of approximately 4 million solar masses confined within a volume no larger than a few times the distance from our Sun to the nearest star. No cluster of compact objects, no dense ball of dark matter, no alternative explanation survives careful scrutiny. The only object consistent with all the observations is a black hole. And then the Event Horizon Telescope confirmed it directly. An image showing the shadow of the event horizon against the glowing background of accreting plasma. The shadow's size matches the predicted size for a black hole of that mass, with a precision that leaves no room for alternative interpretations. Then there are gravitational waves. On the 14th of September, 2015, at 5:51 in the morning, Eastern Time, the LIGO detector in Livingston, Louisiana, detected a signal. 7 milliseconds later, The LIGO detector in Hanford, Washington, detected the same signal. The signal was a chirp, a rapid oscillation that rose in frequency and amplitude over a fraction of a second before cutting off abruptly. The analysis took months. The conclusion was unambiguous. Two black holes, one with a mass of approximately 36 solar masses and another with a mass of approximately 29 solar masses, had been orbiting each other at a significant fraction of the speed of light and had merged. The merger lasted less than a second. The energy released in that final moment was equivalent to approximately 3 solar masses converted directly into gravitational waves, ripples in the fabric of space-time itself, propagating outward at the speed of light, detectable by an instrument 1.5 billion light-years away. Since that first detection, the LIGO-Virgo-CAGRA collaboration has detected over 90 confirmed gravitational wave events, the vast majority of them binary black hole mergers. The gravitational waveforms match the predictions of general relativity to extraordinary precision. Black holes are doing exactly what the equations say they should do. The weight of all of this evidence converges on a fact that would have seemed extraordinary 100 years ago. Black holes are not exotic. They are common. They are a normal product of stellar evolution. They sit at the centers of galaxies. They merge and create new, larger black holes. They are, in the grand inventory of cosmic objects, about as unusual as mountains. And the equations that predict them, Einstein's field equations of general relativity, are among the most precisely tested equations in the history of physics. Every experiment designed to test general relativity has confirmed it. The precession of Mercury's orbit, the bending of starlight around the Sun, first measured during the solar eclipse of 1919, gravitational time dilation, the confirmed fact that clocks run slower in stronger gravitational fields, an effect now routinely corrected for in the GPS system, which would accumulate errors of kilometers per day without the correction. Frame dragging the predicted, measured, confirmed fact that a rotating massive object drags the fabric of space-time around with it as it spins. Every prediction, every test, every measurement confirmed. So when the same equations that produced all of these confirmed predictions, the same equations validated to extraordinary precision across more than a century of experimentation, when those equations also produce a second object, a mathematical structure that looks like a black hole's mirror image, a structure that nobody has ever observed, but that falls out of the mathematics as inevitably as black holes themselves, we are obligated to take it seriously, not to accept it as real, not to assume the universe has built it, but to take it seriously, to ask why it is there, to ask whether the universe has chosen to honor this particular prediction or to ignore it, and to ask what the answer tells us about the universe we actually live in. That second object is what this story is about. And to understand it, you need to follow the mathematics somewhere that physics spent decades refusing to go. Schwarzschild published his solution in 1916 and died shortly after. The solution contained a peculiarity that troubled physicists for years. At the Schwarzschild radius, the radius of what we now call the event horizon, the solution appeared to produce a mathematical singularity, a place where certain terms in the metric became infinite or undefined. Early interpretations of this singularity were confused. Some physicists thought it indicated a real physical catastrophe at that radius. Others thought it was a coordinate artifact, a problem with the mathematical language being used to describe the geometry, not a feature of the geometry itself. The debate went on for decades. It was not until the 1950s and 1960s that mathematicians and physicists worked out how to properly extend the Schwarzschild solution through the event horizon to understand what the geometry was doing on the other side. In 1958, David Finkelstein introduced what are now called Eddington-Finkelstein coordinates, a new mathematical language for describing the Schwarzschild geometry that made the event horizon transparent, in the sense that the coordinates remained well behaved at the horizon and allowed a description of what was happening on both sides. In these coordinates, it became clear that the singularity at the Schwarzschild radius was indeed a coordinate artifact, a product of the particular way the original solution was written, not a feature of the underlying space-time. The event horizon itself was not a place where space-time ended. It was a place where the direction of causal flow changed in the way described earlier. Material could cross it. Light could cross it. What could not happen was any crossing from inside to outside. The event horizon was a one-way membrane in the causal structure of space-time, but Finkelstein's coordinates, while they resolved the confusion at the horizon, still did not reveal the full geometry of the Schwarzschild solution. They could describe an infalling observer crossing the horizon from outside to inside, but there was more structure hiding in the mathematics. The full picture required a more complete extension of the solution, one that would expose something extraordinary. In 1960, Martin Kruskal and, independently, György Sagaras developed a coordinate system now called Kruskal-Sagaras coordinates that extends the Schwarzschild solution to its maximal analytic extent. Maximal analytic extension means the following. You take the equations and you push them as far as they can possibly go in every mathematical direction, filling in every region of space-time that is connected to the original solution without introducing any new singularities or artificial boundaries. You let the mathematics show you everything it is capable of showing. What Kruskal and Sagaras found when they did this is one of the most remarkable results in the history of theoretical physics. The fully extended Schwarzschild solution does not describe two regions of space-time. It describes four. The first region is the exterior universe, the space-time outside the event horizon, the region where we live, the region where all of our observations are made, the region where the gravitational field of the black hole is felt, but from which escape is possible. The second region is the black hole interior, the region inside the event horizon, from which nothing can escape, and where all future directed paths lead toward the singularity. These two regions are what everyone knew about. What the Kruskal-Sagaras extension revealed was a third and a fourth region. The third region is a second exterior universe, a complete, separate region of space-time, also outside an event horizon, also with its own asymptotically flat geometry, mirroring the first exterior universe in the way a reflection mirrors an object. In principle, a second universe, completely disconnected from ours. You cannot travel from our exterior to this second exterior through normal space. The only path between them would be through the interior of the structure. And then there is the fourth region, symmetric to the black hole interior, but with one critical difference. Its causal structure runs in the opposite direction. In the black hole interior, all future directed paths lead toward the singularity. In this fourth region, the white hole interior, all past directed paths lead away from a singularity. In this region, matter and light can only move outward. The horizon bounding this region is an anti-trapping surface. Matter and light can cross it from inside to outside, but nothing from the exterior can ever cross it inward. It is the exact causal opposite of a black hole event horizon. This fourth region is the white hole. It was not invented. Nobody proposed it as a hypothesis and went looking for evidence. It was uncovered, extracted from the mathematics of a solution that had been sitting in the literature since 1916, waiting for someone to push the equations far enough to see what was hiding inside them. The white hole is a direct mathematical consequence of the Schwarzschild solution, as inevitable as the black hole itself. If you accept the equations of general relativity and the observational evidence that those equations are correct is overwhelming, then the white hole is written into the mathematics of the universe with the same authority as the black hole. Let us be precise about what the white hole is, geometrically and physically. A white hole is bounded by an event horizon, but this horizon functions in the opposite direction from a black hole's horizon. In a black hole, the event horizon is a surface that matter and light can cross in only one direction, from outside to inside. Once inside, they cannot return. In a white hole, the event horizon is a surface that matter and light can cross in only one direction, from inside to outside. Nothing from outside can ever cross the white hole horizon inward. Not matter, not light, not any signal. From the outside, a white hole appears as a region from which matter and radiation continuously emerge, but which cannot be entered or influenced from the exterior. The singularity in the white hole is a past singularity, in contrast to the future singularity of a black hole. In a black hole, the singularity lies in the future of every infalling observer. It is where everything inside is eventually headed. In a white hole, the singularity lies in the past. It is the origin point from which everything inside has emerged. Matter in the white hole interior has come from the singularity and is moving outward toward the horizon, beyond which it will enter the exterior universe. The white hole is an object that emits. A black hole is an object that absorbs. They are the same geometry, related by a reversal of the direction of time. This is the precise meaning of time reversal symmetry in this context. Einstein's field equations. The fundamental equations of general relativity are time reversal symmetric. This means that if you have a valid solution to the equations and you replace the time coordinate with its negative, if you run the solution backward in time, you obtain another valid solution. A black hole, run backward in time, becomes a white hole. Every infalling trajectory of matter and light, reversed, becomes an outflowing trajectory. Every future-pointing path that terminates at the singularity, reversed, becomes a past-pointing path that originated from the singularity. The equations cannot distinguish between these two solutions. Both are mathematically valid. Both are equally consistent with the laws of general relativity. The universe, for reasons that will take us the rest of this story to examine, appears to have chosen only one: the connection between the black hole exterior and the white hole interior, the throat linking the two structures through the full Kruskal-Szekeres geometry, is the Einstein-Rosen bridge. Einstein and Rosen first identified this structure in 1935, working from the Schwarzschild solution and recognizing that the geometry contained a connecting passageway between two asymptotically flat regions of spacetime. They were trying to use this structure to build a geometric model of elementary particles, a program that ultimately did not succeed, but the mathematical structure they identified was real and has remained a foundational concept in the study of space-time geometry ever since. The bridge connects the two exterior universes through the interior, a throat of minimal area that, in the fully extended Schwarzschild solution, appears and then pinches off as the black hole interior evolves toward the future singularity. John Archibald Wheeler later gave these structures the name wormholes, a term that has entered the popular imagination so thoroughly that it is sometimes difficult to separate the physics from the science fiction. The physics is specific, technical, and sobering. The science fiction is easy and seductive. This story is about the physics. The first important thing to understand about the Einstein-Rosen bridge is that, in its classical form, it is not traversable. This was demonstrated rigorously by Wheeler and Robert Fuller in 1962, and the result has never been seriously challenged. The argument is relatively straightforward once you understand the Kruskal-Szekeres diagram. In that diagram, the wormhole, the throat connecting the two exterior universes, exists for a moment, then pinches off as the black hole interior evolves. The pinch-off happens so rapidly that even a signal traveling at the speed of light cannot cross the throat before it closes. There is no path through the wormhole that a physical object or signal could follow without violating the speed of light constraint. The bridge exists, but it cannot be used. You cannot travel through it. You cannot send information through it. It opens and closes in a time so short that even light cannot make the crossing. This is a disappointment for science fiction, but it is exactly the kind of precise result that makes the physics interesting. The wormhole is there. The mathematics is unambiguous about its existence, but the physics is equally unambiguous that it cannot be used in its classical form. Why? Because the bridge does not remain open long enough. And why doesn't it remain open? Because the geometry of space-time around a black hole is dynamic. It is evolving. The interior region is collapsing toward the singularity, and the wormhole throat is part of that collapsing interior. It is not a stable, static structure. It is a transient feature of a violently evolving geometry. For the wormhole to remain open long enough to be traversable, something would have to hold it open against the gravitational forces trying to pinch it shut. The theoretical requirement for this was worked out in detail by Kip Thorne, Michael Morris, and Ulvi Yurtsever in 1988. Their analysis showed that a traversable wormhole would require the presence of what they called exotic matter material with negative energy density. Negative energy density is not negative mass in the everyday sense. It refers to matter that violates what physicists call the null energy condition, a requirement satisfied by all known forms of matter and energy, that the local energy density, as measured by any observer moving along a light ray, must be non-negative. Exotic matter, by definition, would violate this condition. It would have a negative energy density in a sense that would produce a repulsive gravitational effect capable of holding the wormhole throat open. Does exotic matter exist? In a very limited sense. Quantum mechanics allows for regions of space with negative energy density through effects like the Casimir effect, a measurable attractive force between two uncharged, parallel conducting plates in a vacuum, arising from the fact that the region between the plates has fewer quantum vacuum fluctuations than the region outside, producing a small negative energy density relative to the vacuum. This effect has been confirmed experimentally. But the magnitude of the Casimir effect is extraordinarily small, and there is no confirmed mechanism by which exotic matter, in the quantities required to hold a macroscopic wormhole open, could be created or sustained. As of 2026, no exotic matter in sufficient quantities to support a traversable wormhole has been identified anywhere in the observable universe. The traversable wormhole remains a theoretical possibility that the known universe does not appear to have constructed, at least not at any scale we can detect. All of this, the Schwarzschild solution, the Kruskal-Saccharis extension, the white hole interior, the Einstein-Rosen bridge, the instability of the classical wormhole, the requirement for exotic matter is established mathematics. It is not speculation. It is the direct output of equations that have been tested, validated, and confirmed more thoroughly than almost any other framework in the history of physics. And all of it is pointing at the same extraordinary conclusion. The equations of general relativity demand a universe in which black holes have mathematical partners, partners that have never been observed, partners that the universe, by all appearances, has chosen not to build or has chosen to hide so thoroughly that we have never found them. That gap between what the mathematics requires and what the observations show is not a footnote. It is the central mystery of this story. And here is what makes that mystery so urgent. Black holes are real. They are confirmed. They are among the most powerful and most prevalent structures in the universe. Their discovery validated general relativity in one of its most dramatic predictions. And the same equations that made black holes inevitable, the same mathematical framework that passed every test we threw at it for over a century, also made white holes inevitable. If the equations were right about the one, we have to explain why they appear to be wrong about the other. Or we have to explain why the universe is hiding the other from us. Or, and this is the possibility that modern physics is beginning to take seriously, we have to accept that we have been misunderstanding what the other actually is and where it actually hides, and on what timescales it actually operates. The answer to that question is not in the coordinates. It is not in the geometry. It is not in any extension of classical general relativity, no matter how carefully done. The answer is in what happens at the singularity, the point at the center of every black hole where general relativity breaks down and falls silent. To understand white holes, you have to understand what replaces the singularity when you apply the laws of quantum mechanics to a region of infinitely curved spacetime. That is a story for later in this documentary. But to get there, you first need to see what the white hole actually demands of the physics, what properties the mathematics assigns to it, why those properties make it so difficult to reconcile with the universe we observe, and why the question of whether white holes exist is one of the deepest open questions in theoretical physics today. The equations have been speaking for more than 100 years. The geometry has been waiting. Everything we have established in this first part of the story is the foundation, the confirmed, measured, photographed, gravitational wave-detected reality of black holes, and the mathematical inevitability written into the same equations of their mirror image. But a mirror image in the mathematics of space-time is not the same as a mirror image in the universe. The universe gets to choose which solutions it builds, and figuring out what choice the universe has made and why requires going deeper into the geometry than anyone went for the first 4 decades after Schwarzschild wrote down his solution. That geometry is where we are going next, and what it reveals about the structure of space-time about what is hiding inside the Schwarzschild solution, about what the full picture of a black hole actually looks like, about the object that is written into the equations with the same inevitability as the black hole itself, is one of the most extraordinary things in the entire history of mathematical physics. In 1935, Albert Einstein and Nathan Rosen sat down with the Schwarzschild solution and did something that would not be fully understood for 25 years. They extended it. They pushed the mathematics further than Schwarzschild had gone, and what they found, embedded in the geometry of a black hole, was a bridge. Not a bridge in any ordinary sense. A bridge through space-time, a passage connecting two separate regions of the universe through the throat of a black hole's geometry. They called it a bridge. The rest of physics would eventually call it a wormhole. And what sits on the other end of that bridge, written into the equations with perfect mathematical symmetry, is a white hole. To understand what Einstein and Rosen actually found, you need to understand what they were looking at. The Schwarzschild solution, as originally written, describes the geometry of space-time outside a spherically symmetric, non-rotating, electrically neutral mass. In those coordinates, the coordinates Schwarzschild used in 1916, which use a time variable measured by a distant observer and a radial variable measuring distance from the center, the solution appears to behave badly at two locations: at the center, where the curvature becomes infinite, and at the Schwarzschild radius, where certain terms in the metric become infinite or zero, in a way that seemed, to early readers, to indicate a genuine physical crisis at that radius. The behavior at the Schwarzschild radius puzzled physicists for a long time. Arthur Eddington, one of the leading relativists of the early 20th century, recognized in the 1920s that the singularity at the Schwarzschild radius was almost certainly a coordinate artifact, a product of the mathematical language being used, not of the physics itself. He proposed an alternative set of coordinates that made the behavior at the horizon cleaner. But this was not widely appreciated, and the nature of the Schwarzschild radius remained a subject of confusion and debate for several more decades. Einstein himself was among those who were uncertain. He was deeply uncomfortable with singularities. In general, he believed, throughout most of his life, that a complete and consistent theory of physics should not contain points where quantities become infinite or where the theory breaks down. The singularity at the center of the Schwarzschild solution was deeply troubling to him for this reason. The apparent singularity at the Schwarzschild radius was, he thought, either an artifact or a signal that the Schwarzschild solution was being applied beyond its domain of validity. When Einstein and Rosen examined the solution together in 1935, they noticed something that had been present in the mathematics all along, but had never been given its proper geometric interpretation. The Schwarzschild solution, when examined carefully, describes not one region of space-time but two. On one side of the Schwarzschild radius, there is the familiar exterior, the region where gravitational fields are finite, where matter can exist and move, where distant stars and galaxies send light outward. On the other side, in a mathematical sense, a region that the Schwarzschild coordinates do not directly reach, but that emerges when you look at the full analytic structure of the solution. There is a second region, a second, asymptotically flat exterior, topologically identical to the first, connected to it through the geometry at and inside the Schwarzschild radius. Einstein and Rosen called the connection between these two regions a bridge. What they were describing, in geometric terms, is a throat, a region where The spatial cross-section of the four-dimensional spacetime contracts to a minimum before expanding outward again toward the second exterior. In the spatial geometry, it looks like a narrow passage connecting two large, open regions. In the full spacetime geometry, it is more complex. The bridge is not a static tunnel, but a dynamic structure that evolves in time. But the essential topology is that of a connection, two separate exterior universes linked through the interior of the structure. Einstein and Rosen's motivation for this work was not to predict the existence of white holes or to understand the causal structure of black holes. They were trying to build a unified field theory, a geometrodynamics program in which elementary particles like electrons and protons were modeled as geometric structures in spacetime rather than as point masses. The bridge offered a possible model. A particle could be thought of as a wormhole connecting two distant regions with electric charge flowing through the throat. This program ultimately failed, and the paper is now remembered not for the unified field theory it proposed, but for the geometric structure it identified. The Einstein-Rosen bridge became one of the most studied objects in the history of theoretical physics. But the full geometric meaning of the bridge and the full structure of what it connects was not understood until Martin Kruskal and György Sekeres developed their coordinates in 1960. What they did and why it changed everything requires a brief technical description that will be worth every second of attention. The problem with the Schwarzschild coordinates, the original coordinates used in 1916, is that they cover only part of the full spacetime. They describe the exterior of the black hole and, with some mathematical pushing, the future interior, the region inside the event horizon that leads to the singularity. But they do not, as written, describe the full global structure of the geometry. The Schwarzschild coordinates have what mathematicians call a coordinate singularity at the event horizon. The coordinates misbehave there in a way that does not reflect any physical singularity in the spacetime. Once you recognize this and change to coordinates that do not break down at the horizon, you can ask, what is the full, maximal, analytic extension of this spacetime? What is the largest spacetime that is consistent with the Einstein field equations and that contains the Schwarzschild solution as a subset? That is the question Kruskal and Sekeres answered. Their coordinates cover the entire maximally extended Schwarzschild spacetime, and the picture they reveal has four distinct regions. Call them Region 1 through Region 4. Region 1 is the exterior universe, the spacetime outside the future event horizon of the black hole. This is the region we live in, the region from which all our observations are made. It extends from the event horizon outward to spatial infinity in all directions. It is asymptotically flat, meaning that far from the black hole, spacetime looks like ordinary, uncurved flat spacetime. Mass is present only in the compact region near the center. Region 2 is the future interior of the black hole, the region inside the event horizon, bounded in the future by the singularity. Every world line, every possible trajectory of a physical observer that enters Region 2 from Region 1 is directed toward the singularity. There is no escape. The singularity is not a point in space that you approach and then stop at. It is a moment in the future from which no further future exists. In the Kruskal diagram, it appears as a boundary of the spacetime, a wall above which the geometry ceases to be defined. Region 3 is the second exterior universe, a complete, separate, asymptotically flat region of spacetime, topologically identical to region 1, connected to the rest of the geometry through the interior. Region 3 is causally disconnected from region 1. No signal can travel from region 3 to region 1, or vice versa, through the interior of the geometry. They are connected by the space-time, but causally isolated from each other. An observer in region 1 cannot receive any signal from region 3, and an observer in region 3 cannot receive any signal from region 1. Region 4 is the white hole interior. It is bounded below by the past singularity, the time reverse of the black hole's future singularity. Every world line in region 4 that approaches the singularity from above is past directed, meaning the singularity is in the past, not the future, of observers in this region. From region 4, matter and light can cross the event horizon outward into region 1 or into region 3, but nothing from region 1 or region 3 can cross the horizon inward into region 4. The causal structure is the exact mirror image of the black hole interior. This is the white hole. It occupies region 4 of the fully extended Schwarzschild spacetime. Its horizon is a past horizon, an anti-trapping surface, in contrast to the future horizon, the trapping surface of the black hole. The terminology of anti-trapping and trapping refers to the behavior of light rays near the horizon. Near the black hole horizon, both ingoing and outgoing light rays are trapped. Both directions of radially emitted light converge toward the singularity. Near the white hole horizon, both ingoing and outgoing light rays diverge. Both directions of radially emitted light spread outward. This is a precise geometric characterization of the difference between the two structures, and it has observational consequences that, at least in principle, could distinguish them. The Kruskal diagram, the standard visual representation of this four-region spacetime, is one of the most important pictures in the history of theoretical physics. In it, the spacetime is drawn as a square, rotated 45 degrees to look like a diamond. The two event horizons, the future horizon of the black hole and the past horizon of the white hole, cross at the center of the diamond, dividing it into four triangular regions. The future singularity appears as a curved line across the top of the diagram above region 2. The past singularity appears as a curved line across the bottom of the diagram below region 4. Region 1 occupies the right side of the diamond. Region 3 occupies the left side. The full structure is symmetric, under a reflection that exchanges top and bottom, the exchange that corresponds to time reversal. The black hole is above the center. The white hole is below. They share the same event horizon, approached from different sides and crossed in different directions. The Penrose diagram, a conformal compactification of the Kruskal diagram that brings infinity to finite coordinate values, makes the causal structure even more transparent. In the Penrose diagram, light travels at 45-degree angles. The event horizons of the black hole and white hole are both diagonal lines, and the regions they bound are immediately visible. The black hole interior is above both horizons. The white hole interior is below both horizons. And the two exterior universes sit on either side, each extending to their own spatial and temporal infinities. Understanding this diagram makes the white hole's properties obvious in a way that a verbal description alone cannot achieve. The white hole is not in a different place in space from the black hole. It is in a different place in time, or more precisely, in the causal structure of the space-time. It is the same event horizon approached from the inside as a past boundary rather than crossed from the outside as a future barrier. The geometry is the same, the mass parameter is the same, the space-time curvature around the horizon is the same. The only difference is the direction of causal flow. This brings us to the most important single fact about white holes that this entire story depends on. A white hole is not a separate object from a black hole. It is the same geometric structure, examined from a different side and a different temporal direction. When physicists say that a white hole is the time reversal of a black hole, they are not speaking loosely or metaphorically. They are saying something precise. If you take the full Kruskal-Sekerres geometry of the Schwarzschild spacetime and you apply the operation of replacing every instance of the time coordinate with its negative, a mathematical operation that represents reversing the direction of time, you obtain another valid solution to the Einstein field equations. And in that solution, the roles of the black hole interior and the white hole interior are exchanged. What was the black hole becomes the white hole, and vice versa. This is not a curiosity. It is a fundamental symmetry of the equations. Einstein's field equations are symmetric under time reversal in vacuum, meaning that if space-time is governed by general relativity in the absence of matter, then any solution to the equations remains a solution when time is reversed. The black hole and the white hole are related by this symmetry. They are the two time reversal partners of the same geometry. If the laws of physics are truly time reversal symmetric, and in the regime described by general relativity in vacuum, they are, then, the existence of one demands the existence of the other, in the same sense that the existence of any physical process demands that the time-reversed process is also permitted by the laws of physics. Whether the universe actually builds both is a different question entirely, and it is precisely the gap between what the laws of physics permit and what the universe appears to have chosen that defines the deepest problem in this story. Let us press harder on what the white hole's properties actually require. The first property is the one already described. Nothing from the exterior can enter the white hole. This is a causal statement, not a statement about force or barrier. There is no wall preventing entry. There is no repulsive field pushing objects away. What the white hole does is more subtle and more absolute. The geometry of spacetime in its vicinity is such that no future-directed causal curve, no path through spacetime that moves at or below the speed of light in the forward time direction can cross the white hole horizon from the exterior into the interior. It is impossible, not because anything blocks the path, but because the geometry of spacetime forbids it, in exactly the same way that the geometry of spacetime inside a black hole forbids escape. The second property is that matter and radiation from the white hole interior can cross the horizon outward. An observer who begins inside the white hole will be carried outward by the geometry, crossing the horizon and entering the exterior universe. This matter appears to the exterior observer to emerge from the horizon to pour out of a region of spacetime from which no information can return. From the exterior, it looks like an object that spontaneously produces matter and radiation while being impossible to probe or influence. It is exactly the opposite of a black hole in observational terms. The third property is the thermodynamic one, and it is the property that creates the most fundamental difficulty for understanding how white holes could exist in the universe we observe. The white hole's singularity is a past singularity. This means that the origin of all the matter in the white hole interior lies at a single point in the past, the singularity, Everything inside the white hole has emerged from that initial state. This is thermodynamically backwards. In the universe we observe, physical systems evolve from ordered states toward disordered states. The entropy of a closed system increases over time. A past singularity, an initial state of infinite density and curvature, from which matter spontaneously emerges in an organized, outflowing configuration, corresponds to a state of extraordinarily low entropy at the singularity, decreasing entropy in the forward time direction through the interior, and then increasing entropy again once matter crosses the horizon into the exterior. This is a profound violation of the thermodynamic arrow of time as we understand it in every other context in physics. This thermodynamic problem is not a minor technical issue. It is a deep structural mismatch between the white hole's properties and the behavior of every other physical system we have ever observed. In every other domain of physics, classical mechanics, thermodynamics, electrodynamics, quantum mechanics, the equations are also time reversal symmetric, but the actual behavior of systems is not. Entropy increases. Disorder spreads. Things do not spontaneously organize themselves. The arrow of time is real, and it is consistent across everything we observe. A classical white hole would violate this arrow in a dramatic and unmistakable way. It would not merely be surprising. It would be the most spectacular thermodynamic anomaly ever observed, and yet no such anomaly has been detected. Stephen Hawking engaged with this problem from a different and deeply illuminating direction. Hawking's work in the 1970s established that black holes are not entirely black. They emit a faint thermal radiation, now called Hawking radiation, arising from quantum effects near the event horizon. The mechanism is subtle. Pairs of virtual particles near the horizon can be separated by the tidal effects of the intense gravitational field, with one particle falling into the black hole and the other escaping to infinity as real radiation. Over an astronomically long time, this process causes the black hole to gradually lose mass and eventually evaporate entirely. Hawking radiation has not been directly observed. It is predicted to be far too faint to detect for any black hole of astrophysical mass, but the theoretical argument is widely accepted as sound, and it has important implications for the black hole-white hole connection. Hawking pointed out that a black hole, in thermal equilibrium, absorbing radiation from its surrounding environment at the same rate it emits Hawking radiation, would be in a time reversal invariant state. A thermal equilibrium state looks the same whether time is running forward or backward, and the time reversal of a black hole in thermal equilibrium is, by definition, a white hole in thermal equilibrium. This is a remarkable observation. Under the specific conditions of thermal equilibrium with a radiation bath, the distinction between a black hole and a white hole becomes, in a certain sense, operationally meaningless. Each is absorbing and emitting radiation at equivalent rates. The geometry at the horizon is evolving in a time-symmetric way. The two objects are, in some sense, the same object, viewed from different temporal perspectives. This is not a resolution of the problem of white holes. It does not explain why white holes do not appear to exist in our universe, or how they could form, or what would produce one. But it is a suggestive connection, a hint that under certain quantum conditions, the strict distinction between the black hole and the white hole might dissolve. That hint will become important later in this story, when we examine what quantum gravity predicts for the interior of a black hole. Before we get there, however, We need to examine the Einstein-Rosen bridge more carefully, because the bridge is the connection between the black hole and the white hole in the geometry, and understanding its properties is essential to understanding why the mathematical structure of the Kruskal-Sekaris spacetime is so extraordinary and so difficult to reconcile with the physics of the universe we actually inhabit. In the Kruskal diagram, the Einstein-Rosen bridge appears as the spatial cross-section taken at the moment of time symmetry, the horizontal line passing through the center of the diamond. At the moment when the geometry is at its most symmetric between past and future. At this moment, the two exterior universes, Region 1 and Region 3, are connected through a throat of minimum area. The throat is not at the event horizon. It is in the interior, between the two horizons. The geometry at the throat is like a pinched tube. The spatial cross-section contracts from the full size of the two exterior universes down to a minimum, then expands again outward toward the other exterior. This minimum is the wormhole throat. The throat exists for an instant. In the Kruskal diagram, if you move away from the moment of time symmetry, either toward the future or toward the past, the geometry evolves. Moving toward the future, the black hole interior collapses toward the future singularity. Moving toward the past, the white hole interior expands away from the past singularity. The throat of the bridge is squeezed by this evolution. As time advances, the throat pinches off. It closes faster than any signal traveling at the speed of light can cross it. This is the mathematical demonstration of why the Einstein-Rosen bridge is not traversable. The bridge closes before light can traverse it. The closure time, the time available for a signal to traverse the bridge before it pinches shut, is not something that can be extended by any clever choice of trajectory. It is set by the geometry of the space-time, which is in turn set by the Einstein field equations. No matter how you approach the throat, no matter what direction you travel within it, the future singularity closes in before any signal can reach the other side. This is not a technological limitation. It is a geometric one. The laws of physics applied to this geometry forbid the transit. The bridge exists, but it is a bridge that opens for an infinitely short time and then snaps shut, leaving nothing on the other side. There is one escape from this conclusion, and it requires exotic matter. If the wormhole throat could be held open, if something could be inserted into the geometry to prevent it from closing, then a traversable wormhole might be possible. Kip Thorne, Michael Morris, and Olvi Yurtsever showed in 1988 that the energy conditions required to hold a wormhole throat open violate the null energy condition. The requirement that the energy momentum tensor satisfies a certain positivity condition along any null direction. All known classical forms of matter satisfy this condition. To hold a wormhole open, you would need exotic matter that violates it. The Casimir effect, as mentioned, produces regions of negative energy density at quantum scales. Some theorists have explored whether Casimir-like effects could be harnessed to provide the exotic matter needed to hold a wormhole open. The calculations are not encouraging. The amounts of negative energy density required for a macroscopic traversable wormhole are enormous, vastly exceeding anything producible by the Casimir effect or any other known quantum phenomenon. And there is a deeper issue. It is not clear that exotic matter, even if it exists in principle, can be collected and stabilized in the geometry of a wormhole throat without immediately causing the geometry to collapse into a singularity. The requirements are extremely delicate, and the known physics does not provide a plausible path to satisfying them. This is where the classical picture leaves us. The white hole is mathematically inevitable. The Einstein-Rosen bridge, connecting it to the black hole, is mathematically present. But the bridge cannot be traversed. The white hole has no known formation mechanism. Classical white holes are thermodynamically backwards and physically unstable, and no white hole has ever been observed. The equations contain the object. The universe does not appear to have built it, not in any form we can detect. And the classical version of general relativity, pushed as far as it can go, offers no resolution to this discrepancy. But something important is missing from the classical picture. Something that was missing from the beginning, hiding behind the singularity. General relativity, by its own admission, breaks down at the singularity. The singularity is the theory's confession that it is incomplete. A more complete theory, one that incorporates the principles of quantum mechanics into the description of curved spacetime, should replace the singularity with something that makes physical sense. And what that replacement turns out to be may change everything about how we understand the relationship between black holes and white holes. This is not a small technical point. The singularity at the center of a black hole is precisely the region that connects the black hole interior, region 2, in the Kruskal diagram, to the white hole interior, region 4. In the classical geometry, that connection passes through the singularity, where the physics is undefined. In a complete quantum theory of gravity, the singularity is replaced by something else, and the nature of that replacement determines whether the white hole is actually accessible from the black hole, whether the bridge that exists in the mathematics can become, under the right quantum conditions, something real in the physics. That question, what replaces the singularity, and what it implies for the fate of matter inside a black hole, and whether the white hole is a genuine cosmic object waiting to be understood, rather than a mathematical ghost waiting to be dismissed, is the question that the most advanced and most daring work in theoretical physics is currently trying to answer. The equations have been pointing at it for over a century. The observations have been silent about it for the same period. The answer, when it comes, will be one of the most significant results in the history of physics. We have laid out everything that general relativity knows. The black hole is real. The white hole is mathematically inevitable. The bridge between them is present but not traversable by any classical means. The singularity is the place where the classical picture ends. And the universe is presenting us with an object that the equations demand, in a universe that appears never to have built one, or that has built it in a form so different from what we expected, that we have been looking in entirely the wrong place, in entirely the wrong way, at entirely the wrong time scales. That is the mystery, and the mystery begins to unravel in the most unlikely of places, not in the geometry of the exterior, not in the behavior of matter near the event horizon, but at the very bottom of the black hole, at the singularity itself, where general relativity surrenders and quantum gravity begins. The universe is under no obligation to build everything its equations permit. This is one of the most important distinctions in all of physics, and it is the distinction that makes the question of white holes so genuinely difficult. General relativity's equations permit a great many things that the universe does not appear to have constructed. They permit negative mass objects. They permit closed time-like curves paths through space-time that loop back on themselves, allowing an observer to return to their own past. They permit the full, maximally extended Schwarzschild space-time with its 4 regions and its wormhole throat and its white hole interior. The equations are permissive. The universe is selective. And the question of what principle governs the universe's selections, what physics decides which solutions get built and which do not, is one of the most productive sources of insight in the entire history of theoretical science. For white holes, the principle that appears to exclude them from the universe we observe is not a single rule. It is a convergence of three separate problems, each serious enough on its own to make white holes deeply implausible in their classical form, and all three together, creating a case against classical white holes that is difficult to argue with. The first problem is dynamical, the second is thermodynamic, the third is formative. Together, they tell us that classical white holes are not merely rare or hard to observe. They are physically unreasonable objects whose properties are so radically at odds with the behavior of matter and space-time in the universe. We inhabit that their existence in the classical form would require the universe to behave in ways that appear to violate its own deepest operating principles. Begin with the dynamical problem, because it is the most immediately physical and the most viscerally convincing. Consider a white hole sitting in space. By definition, it is a region from which matter and radiation continuously emerge. It has a gravitational field because it has mass, and mass curves space-time, regardless of whether the object is a black hole or a white hole. That gravitational field attracts surrounding matter. Gas, clouds, dust particles, photons passing nearby, all of these are pulled toward the white hole by its gravity. They accelerate toward it. They approach the event horizon. And here is where the dynamics become catastrophic. As material from the exterior approaches the white hole's horizon, it cannot enter the causal structure of the white hole prevents it. But it can accumulate. It gathers at the horizon, pile upon pile of infalling matter that has been gravitationally attracted to the white hole, but cannot cross the boundary. As this material compresses and accumulates, it forms what physicists call a blue sheet, a layer of matter that has been falling inward at high velocity and has had its radiation blue shifted to enormous energies by the intense gravitational field. The energy density of this blue sheet grows without bound. The pressure it exerts on the horizon increases without limit. And the result, as was demonstrated rigorously in work by William Israel and others in the 1976 through 1980 period, is that the white hole is immediately destabilized. The accumulated matter collapses into a new black hole centered on the white hole, overwhelming and destroying it. A classical white hole that continuously ejects matter cannot survive the gravitational consequences of its own attraction. It is self-defeating. The very property that defines it, the emergence of matter from its interior, produces the conditions for its own annihilation. This is not a subtle effect. It is not something that might be circumvented with clever engineering or exotic initial conditions. It is a direct consequence of the gravitational field that any white hole must have by virtue of having mass. The blue sheet instability is generic. It applies to any white hole of any mass in any environment that contains even the smallest amount of surrounding matter or radiation. In the universe we observe, which is filled with the cosmic microwave background radiation permeating all of space at a temperature of approximately 2.7 Kelvin, which is filled with intergalactic gas and dust and photons from billions of galaxies. There is no location that is empty enough to allow a classical white hole to persist without immediately accreting surrounding material and triggering this instability. A classical, continuously ejecting white hole cannot survive in our universe. It would be destroyed the moment it came into contact with any of the matter and radiation that permeate cosmic space. Given that such matter and radiation are everywhere, the survival time of a classical white hole in our universe is effectively zero. This is the dynamical problem, but it is actually the least fundamental of the three, because it concerns the practical stability of white holes rather than their deeper physical coherence. The thermodynamic problem cuts deeper, and it concerns not whether white holes can survive, but whether they are consistent with the most fundamental arrow of directionality in all of physics. Thermodynamics, in its most essential formulation, is the study of why things happen in one direction and not the other. An egg can be dropped on the floor and shatter into 1,000 pieces, but 1,000 pieces of egg have never spontaneously assembled themselves on the floor, leaped upward, and reassembled into a perfect egg in midair. The first event happens, the second does not. Both are permitted by Newton's laws of motion, which are also time reversal symmetric. Both conserve energy, both conserve momentum. The laws of mechanics do not distinguish between them, but something does. That something is the second law of thermodynamics. The entropy of a closed system never decreases over time. The shattered egg has higher entropy than the intact egg. Physical processes move from lower entropy to higher entropy, not the other way around. This is the thermodynamic arrow of time, and it is one of the deepest regularities in all of physics. It is why we remember the past, but not the future. It is why we can burn wood, but cannot unburn it. It is why the universe has a definite direction of temporal evolution, despite the fact that the fundamental laws of mechanics are symmetric in time. A classical white hole violates this arrow. Its singularity is a past singularity, a state of infinite density and curvature in the past from which all the matter in the white hole interior has emerged. That past singularity corresponds to an extraordinarily low entropy initial state. As time advances forward from that singularity, matter flows outward from the white hole interior, crosses the horizon, and enters the exterior universe. The entropy of the system increases as matter disperses into the exterior. But the starting point, the past singularity, was a state of incredibly low entropy, and physical processes do not start in low entropy states spontaneously. They have to be set up in low entropy states by some prior physical process. In the universe, we observe low entropy initial states require explanation. The Big Bang itself is understood as an extraordinarily low entropy initial condition, and explaining why the Big Bang began in such a state is one of the deepest open problems in cosmology. A white hole would require an equally extraordinary low entropy initial condition at its past singularity, with no known physical mechanism to produce it. This is a much more serious problem than it might initially appear, because it is not just about whether white holes are likely, it is about whether they are coherent with the thermodynamic structure of the universe we inhabit. The universe we observe has a thermodynamic arrow. Entropy increases from past to future. A classical white hole has a thermodynamic arrow running in the same direction. Entropy increases from its past singularity outward toward the future, but it has been initialized in a low entropy state that has no known origin. Creating a white hole in the real universe would require either violating the second law of thermodynamics somewhere upstream in the process that creates the initial low entropy condition, or accepting that the universe spontaneously produces low entropy initial states, which is precisely what the second law tells us does not happen. Either way, the classical white hole is thermodynamically pathological. Roger Penrose, who spent much of his career thinking about the relationship between singularities, entropy, and the arrow of time, proposed a principle called the Weyl curvature hypothesis, the idea that the specific type of space-time curvature associated with gravitational degrees of freedom, called the Weyl curvature, must be very low at past singularities and can be very high at future singularities. This hypothesis, if correct, provides a geometric characterization of the thermodynamic arrow of time. Past singularities, corresponding to low entropy, have low Weyl curvature, while future singularities, corresponding to high entropy, have high Weyl curvature. The Big Bang singularity, as a past singularity, should have low Weyl curvature, and observations of the cosmic microwave background, which show the early universe to be extraordinarily uniform and homogeneous, are consistent with this. The future singularity inside a black hole, corresponding to a state of maximal entropy for the infalling matter, should have high Weyl curvature, and the mathematics of the black hole interior is consistent with this as well. A white hole's past singularity, in Penrose's framework, should have low Weyl curvature. This is consistent with the thermodynamic picture. The past singularity is a low entropy state, but it raises a devastating question. Why? What physical process produced this low entropy initial state? For the Big Bang, the question of initial conditions is hard, but at least framed within a cosmological context where the entire universe began from a single event. For a white hole appearing somewhere in the mature universe billions of years after the Big Bang, in a cosmos that has already evolved to a state of considerably higher entropy than its origin, there is no plausible mechanism to produce the extraordinarily low entropy initial condition that the white hole's past singularity would require. The universe does not spontaneously generate pockets of extreme low entropy in the middle of its evolution. Doing so would violate the second law of thermodynamics as comprehensively as any physical process we can imagine. The third problem is the formative problem, and it is perhaps the cleanest of the three. Black holes have a well-understood formation mechanism. A massive star, any star with a mass greater than roughly 25 times the mass of our Sun, depending on its composition and the details of its evolution, exhausts its nuclear fuel, can no longer sustain the pressure needed to support its own gravity, and undergoes catastrophic gravitational collapse. The collapse happens on a time scale of milliseconds. The core implodes, forming a black hole. The envelope is expelled in a supernova explosion. This process has been observed. The supernovae are seen. The black hole remnants are detected. The mechanism is not hypothetical. It is astrophysics. White holes have no analogous mechanism. There is no known astrophysical process that would create a white hole from realistic initial conditions in our universe. A white hole, as we have established, begins with a past singularity, a state of infinite density in the past, from which matter spontaneously emerges. To create such an object from ordinary matter in the ordinary universe, you would need to initiate a reverse gravitational collapse. You would need a region of matter that spontaneously begins flying outward from a point of infinite density, decreasing in density as it expands. No known physical process triggers this. No known astrophysical event, no stellar process, no quantum effect in the standard model of particle physics produces a past singularity surrounded by an anti-trapping horizon. The white hole, in its classical form, simply has no origin story. It appears in the mathematics of the full Schwarzschild spacetime as a permanent feature of the geometry present from the infinitely remote past, eternal, in the same idealized sense that the maximally extended Schwarzschild space-time is eternal. But in the real universe, where space-time is not eternally static but is dynamically evolving, where stars form and collapse, and where black holes grow by accretion, the classical white hole has no home. There is a proposed resolution to the formative problem that has attracted serious attention in the literature, though it remains a minority hypothesis. It was worked out in detail in a paper published in Physics Letters B in 2011 by Alon Retter and Shlomo Heller, building on earlier ideas by Igor Novikov in the 1960s and Yuval Neeman. The proposal is as follows. Rather than continuously ejecting matter, a white hole ejects all of its matter in a single instantaneous burst, a small bang, in Retter and Heller's terminology. In this picture, the white hole is not a persistent, continuously emitting object that must survive in the harsh environment of the real universe. It is a single, explosive event like the Big Bang, but smaller, localized, and occurring at a specific point in space, at a specific moment in time. All of the matter and energy that was ever inside the white hole is released in one pulse, and then the white hole ceases to exist. This proposal sidesteps the blue sheet instability, since the white hole does not persist long enough to accumulate surrounding matter. There is no accreted material to form the destabilizing blue sheet. The explosion happens before any surrounding matter can fall in. It also sidesteps, at least partially, the thermodynamic problem. The white hole is not a long-lived structure that must maintain a low entropy state against the thermodynamic pressures of a high entropy environment, but a transient event that begins and ends before thermodynamic equilibration can occur. Retter and Heller went further and proposed an observational connection. They suggested that certain gamma-ray bursts, the most energetic transient explosions observed in the universe, events that release more energy in seconds than the sun will radiate over its entire 10 billion year lifetime, might be signatures of small bang white holes. Gamma-ray bursts are detected from cosmological distances. They come in two main classes: short gamma-ray bursts, lasting less than 2 seconds, and long gamma-ray bursts, lasting longer. The standard models attribute short gamma-ray bursts to mergers of compact objects such as neutron star binary systems, and long gamma-ray bursts to the collapse of massive stars. Retter and Heller proposed that a third class, or perhaps a subset of the observed bursts, might be produced by white hole explosion events, where the single pulse of matter ejection produces the gamma-ray burst as its electromagnetic signature. This hypothesis is speculative. It has not been confirmed. No gamma-ray burst has been positively identified as a white hole event, and the standard models for gamma-ray bursts explain the observed data adequately without invoking white holes. But the proposal is not frivolous. It appeared in peer-reviewed scientific literature. It makes a testable prediction about the statistical properties of gamma-ray bursts, and it identifies a class of events that could, in principle, be produced by white holes if they exist and if the small bang model is correct. It represents exactly the kind of work that theorists must do to move a hypothesis from pure mathematics to empirical science. Find an observable consequence, identify candidate events, and design tests that could in principle falsify the prediction. The tests have not yet been conclusive either way. The small bang proposal also connects to one of the most audacious ideas in the entire white hole literature, the suggestion that the Big Bang itself was a white hole event. This idea has a long history. It was anticipated by Novikov's lagging cause concept in the 1960s, which described white holes as remnants of the Big Bang that had lagged behind in their expansion, delayed in their emergence, finally exploding into the universe long after the initial event. In this picture, the Big Bang was the ultimate white hole, a past singularity from which all of the matter and energy of the observable universe emerged in a single explosive event. The low entropy initial condition required by a white hole singularity is simply the low entropy initial condition of the Big Bang, which is the deepest thermodynamic mystery in all of cosmology. If the Big Bang was a white hole, then the thermodynamic problem for white holes dissolves into the thermodynamic problem for the Big Bang, not a resolution, but a reframing that at least places all the difficulties in one place. This is a minority view among cosmologists. The standard cosmological model, the lambda cold dark matter model, confirmed with extraordinary precision by observations of the cosmic microwave background and the large-scale structure of the universe, does not model the Big Bang as a white hole event. The initial singularity of the standard model is not the same mathematical object as a white hole singularity in the Schwarzschild geometry. The geometries are different, the symmetries are different, the causal structures are different. The analogy is suggestive and has inspired genuine research, but it is not a precise identification, and treating it as one would be misleading. It is a conceptual thread, not a confirmed connection. What all three of these problems, the dynamical instability, the thermodynamic pathology, and the absence of a formation mechanism tell us is something profoundly important about the nature of classical white holes. They are not merely unobserved, they are, in their classical form, physically unreasonable. The equations produce them, the geometry contains them, but the physics of the real universe, the behavior of matter under gravity, the thermodynamic arrow of time, the astrophysical processes that actually create objects in the cosmos, conspires against them with remarkable thoroughness, and yet the equations do not care. The Kruskal-Chakra's geometry does not retract its fourth region simply because the physics of the real universe finds it inconvenient. The white hole is there in the mathematics, sitting in region 4 of the fully extended Schwarzschild spacetime, silent and unobserved, and physically implausible in its classical form, but stubbornly present in the equations. And this persistence is significant, because in the history of physics, equations have been stubbornly right before. The mathematics of quantum mechanics predicted that particles could tunnel through barriers that classical physics said they could not penetrate. The mathematics was right. The equations of general relativity predicted gravitational waves ripples in spacetime before any instrument existed that could detect them. The equations were right. The persistence of white holes in the mathematics of general relativity is not proof that they exist, but it is not nothing. It is a signal that the framework which contains them is pointing at something real, even if we do not yet know what. The resolution to the white hole puzzle, the bridge between the mathematical inevitability of white holes and the physical implausibility of classical white holes, may lie precisely in the place that all three problems converge: the singularity. All three problems with classical white holes are, at their root, problems that involve the singularity. The dynamical instability ultimately concerns the behavior of the geometry near the singularity under quantum corrections. The thermodynamic problem concerns the initial entropy state of the singularity. The formation problem concerns the origin of the singularity. If the singularity is replaced by something else, something that a complete quantum theory of gravity predicts, then all three problems may be transformed simultaneously. The singularity is the pivot point, and understanding what replaces it is the key to understanding whether white holes are a ghost in the machine of general relativity or a genuine feature of how the universe works at its deepest level. That understanding begins with a question that physicists have been wrestling with for decades, a question that sounds almost too simple. What actually happens at the center of a black hole? Not what general relativity says. We already know that general relativity breaks down there and produces an unphysical singularity. What does quantum gravity say? What does the world look like at the center of a black hole when the full machinery of quantum mechanics is brought to bear on the curved space-time geometry? And whatever that machinery produces, whatever replaces the singularity, what does it imply for the other side? What does it imply for the white hole sitting in region 4 of the Kruskal-Sackr's diagram, separated from the black hole interior by the singularity that quantum gravity is now beginning to dissolve? That is the question that the most advanced theoretical physics of the last 2 decades has been building toward. It is a question that has produced results, mathematical results, emerging from serious, peer-reviewed frameworks that are extraordinary in their implications. And it is a question whose answer, if it holds up, suggests that white holes are not ghosts after all. They are not mathematical artifacts that the universe politely ignores. They may be something real, something that every black hole in the universe is already becoming from the inside, at a level below space-time itself, in a transformation so slow and so hidden that the universe has barely begun to show it to us. But to understand how we get there, we first need to understand the framework that makes such a claim possible, a framework that quantizes space-time itself, that replaces the smooth continuum of general relativity with a discrete, granular structure, and that predicts, from first principles, that the singularity at the center of a black hole is not an ending, but a transition. The framework is loop quantum gravity, and what it says about black holes, about singularities, and about what lies on the other side of the deepest darkness in the universe is the story we turn to now. There is a place in the universe where our understanding stops, not because we lack the instruments to look there, not because no telescope is powerful enough or no detector sensitive enough, but because the theoretical framework we use to describe gravity, the most precisely tested physical theory in history, reaches a point at which its own equations return answers that are physically meaningless and then falls silent. That place is the center of a black hole, the singularity, the point where the curvature of space-time becomes formally infinite, where the density of matter exceeds any quantity that physics can describe, where the known laws of physics, every one of them, cease to apply. General relativity's silence at the singularity is not an embarrassment to be glossed over. It is a precise, mathematical admission that something is happening there that the theory cannot describe. And that admission has been, for over half a century, one of the most productive admissions in the history of physics, because it points at the most important unsolved problem in all of theoretical science: the unification of general relativity and quantum mechanics. General relativity describes gravity as the curvature of space-time at macroscopic scales. Quantum mechanics describes the behavior of matter and energy at microscopic scales, the level of atoms, subatomic particles, and the fields that govern their interactions. Both theories are extraordinarily successful within their domains. General relativity correctly predicts the behavior of black holes, the expansion of the universe, gravitational waves, and the deflection of light by massive objects. Quantum mechanics correctly predicts the energy levels of atoms, the behavior of semiconductors, the operation of lasers, the structure of chemical bonds, and the existence of every subatomic particle we have ever discovered. Between them, these two theories account for virtually every physical phenomenon ever observed. And yet, they are fundamentally incompatible with each other in the regime where both are simultaneously relevant, the regime of extremely small scales and extremely strong gravitational fields. The singularity at the center of a black hole is precisely such a regime. The density there, by the time quantum effects become significant, is close to what physicists call the Planck density, approximately 5 times 10 to the 96 kilograms per cubic meter, and the length scales involved are close to the Planck length, approximately 1.6 times 10 to the negative 35 meters. At these scales, both quantum mechanics and general relativity must apply simultaneously, and the lack of a unified theory means we have no reliable description of what happens. Several candidate theories of quantum gravity have been developed over the past several decades. String theory is the most well-known, a framework in which the fundamental objects are not point particles, but one-dimensional strings whose vibrational modes produce the particles of the Standard Model and the graviton, the hypothetical carrier of the gravitational force. Loop quantum gravity is the second major candidate, a framework that takes general relativity's geometric description of gravity seriously and attempts to quantize spacetime itself, to apply the machinery of quantum mechanics directly to the fabric of space and time, treating them not as a smooth continuum, but as a network of discrete quantum units at the Planck scale. Neither theory has been experimentally confirmed. Both are mathematically serious and internally consistent. They make different predictions, and future experiments, if sufficiently sensitive, could in principle distinguish between them. Loop quantum gravity, developed primarily by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin beginning in the late 1980s, reformulates general relativity in variables that are more amenable to quantization. The central mathematical object is not the metric tensor, the standard description of spacetime geometry, but a new set of variables called the Ashtekar variables, which describe the gravitational field in a way that is formally similar to the variables used to describe gauge theories like electromagnetism and the strong nuclear force. In these variables, the quantization of the theory proceeds through the machinery of quantum field theory, producing a quantum theory of spacetime in which the geometry itself, area, volume, length takes on discrete values. There are minimum values of area and volume, the Planck area and the Planck volume, below which the concept of smooth spacetime ceases to be meaningful. Spacetime, in loop quantum gravity, is not a continuous manifold. It is a discrete network of quantum geometric units, a spin network, in the technical language of the theory evolving in time according to quantum mechanical rules. One of the most important predictions of loop quantum gravity concerns what happens at the singularity. In classical general relativity, the singularity arises because the curvature of spacetime grows without bound as you approach the center of a black hole, and the theory has no mechanism to prevent this growth. In loop quantum gravity, the discrete nature of spacetime introduces a natural cutoff. The minimum area and minimum volume of the theory mean that the curvature cannot exceed a certain maximum value roughly the Planck curvature. As the space-time geometry approaches this maximum, the quantum effects of the discrete structure become dominant, producing a repulsive quantum geometric effect that counteracts the classical gravitational collapse. Instead of the curvature growing to infinity and the physics breaking down, the curvature reaches its maximum value and then decreases. The geometry bounces. The collapse is reversed, not by any conventional force, but by the fundamental discreteness of space-time at the quantum scale. This bounce is called the quantum bounce, and it is the central prediction of loop quantum gravity for the interior of a black hole. The quantum bounce replaces the classical singularity with a region of finite density, finite curvature, and well-defined physics, a region where the space-time geometry reaches its most compressed state and then re-expands. The geometry does not end at the singularity, it continues. And the question that naturally follows the question that Abhay Ashtekar, Javier Olmedo, and Parampreet Singh systematically addressed in their research program on loop quantum black holes continues into what? The answer that emerges from the mathematics of loop quantum gravity is remarkable. The Ashtekar-Olmedo-Singh framework, developed in a series of papers beginning in 2018 and continuing into the early 2020s, applies the loop quantum gravity quantum bounce to the interior of a Schwarzschild black hole. The analysis is technical and requires the full machinery of loop quantum cosmology, the application of loop quantum gravity techniques to symmetric cosmological and black hole spacetimes. But the result is clean and striking. When the quantum bounce is applied to the black hole interior, the spacetime geometry after the bounce re-emerges with the causal structure of a white hole interior. The collapse into the black hole singularity is replaced by a quantum bounce at maximum density, after which the geometry expands outward with the structure of region 4 in the Kruskal-Szekeres diagram, the region we have been calling the white hole. This is not a metaphor. It is a mathematical result within the loop quantum gravity framework. The quantum-corrected spacetime of a black hole, when traced from the exterior through the horizon into the interior and through the quantum bounce region, re-emerges as a white hole spacetime. The matter that fell into the black hole, the stars, the gas, the radiation that crossed the event horizon and fell toward the singularity, does not simply stop at the singularity and cease to exist. It passes through the quantum bounce in a region where the known laws of classical physics are suspended and replaced by the quantum geometry of loop quantum gravity, and re-emerges on the other side in the configuration of white hole interior matter, moving outward toward a white hole horizon. The American physicist Carlo Rovelli, one of the founders of loop quantum gravity and one of the researchers who has most clearly articulated the implications of this scenario, described the result in Physics, a review journal of the American Physical Society, in 2018 as follows: "The future of all black holes may be to convert into white holes, from which the matter that fell in can bounce out." The characterization is precise. This is a prediction within the framework of loop quantum gravity, and that framework has not been experimentally confirmed. Rovelli is explicit that the result requires loop quantum gravity to be the correct theory of quantum gravity, and loop quantum gravity is one of several competing theories. But he is also explicit that the mathematical result, given the framework, is robust, and that it provides a genuine quantum gravity prediction that is in principle distinguishable from the classical picture. The timescale for this black-to-white hole transition is an active area of research and debate within the loop quantum gravity community. Different approaches to the problem produce different estimates. Some calculations, using what is called the spin-foam formulation of loop quantum gravity, a covariant, path-integral approach to the theory developed by researchers including Enrico Levine, Roberto Pereira, and Christodoulou and D'Ambrosio, suggest that the transition time scales exponentially with the mass of the black hole. For a stellar mass black hole of perhaps 10 solar masses, the transition time would be incomprehensibly vast, far exceeding not only the current age of the universe, but the time scale for Hawking evaporation, which for a black hole of that mass is already many orders of magnitude longer than the age of the universe. The quantum bounce happens, but it happens in a future so remote that no civilization, no star, no structure we know of will survive long enough to witness it. More recent calculations, including work published in an RCEV preprint in April 2025 by Martin Dussault, and collaborators refining the estimates of Christodoulou and D'Ambrosio, have focused on the relationship between the Hawking evaporation timescale and the bounce timescale. The question is, which process dominates? Does the black hole lose mass primarily through Hawking evaporation and then bounce when it has shrunk to near Planck size? Or does the bounce happen before Hawking evaporation significantly reduces the mass? The analysis suggests that for macroscopic black holes, Hawking evaporation dominates the initial phase, gradually reducing the mass over an astronomical timescale, with the quantum bounce occurring at the final stages when the black hole has been reduced to near Planck mass. In this refined picture, the black-to-white hole transition is not just a quantum gravity prediction, it is the endpoint of Hawking evaporation, the final act in the life cycle of every black hole that forms. This is an extraordinary vision. Every black hole in the universe, every one of the estimated 100 billion trillion black holes scattered through the observable cosmos, is, in this picture, a transient structure, evolving through the stages of accretion and evaporation toward an eventual quantum bounce that will transform it into a white hole, releasing all of the matter and information that ever fell into it back into the universe. The process takes so long that the word long is not nearly adequate. For a black hole of stellar mass, the Hawking evaporation timescale alone is approximately 10 to the 67th years, a number so far beyond any human temporal scale that writing it out has essentially no meaning. The age of the universe is approximately 1.4 times 10 to the 10th years. The Hawking evaporation timescale for a stellar mass black hole exceeds the age of the universe by 57 orders of magnitude. And the quantum bounce follows the evaporation. The white hole that a present-day stellar mass black hole will eventually become is so far in the future that the concept of future barely applies. But, and this is the crucial point, the process happens in principle. The mathematics says it happens. The loop quantum gravity framework, applied consistently to the interior of a black hole, produces a bounce and a white hole on the other side. If the framework is correct, then white holes are not absent from our universe. They are present, but they are the deep future of objects that are currently, from our temporal perspective, in their infancy. Every black hole is a white hole in preparation. The universe is not asymmetric between the two structures. It is sequential. The black hole comes first. The white hole comes after. And the time between the two is so vast that from our position, looking out into a universe that formed its first black holes approximately 1 billion years after the Big Bang, every black hole we observe is in the earliest imaginable stage of its evolution. Not a single one has had time to bounce. Not a single one has had time to become what loop quantum gravity says it eventually will. This is one answer to the question of why we have never observed a white hole. Not because they do not exist, not because the universe has broken its own equations, but because the universe is young, incomprehensibly young, relative to the timescales on which the deepest quantum gravitational processes operate. We are watching the first seconds of a film that runs for longer than any number we have everyday language to express. The March 2025 research from the University of Sheffield, published in Physical Review Letters, approaches the same problem from a different theoretical direction and arrives at a result that is complementary to the loop quantum gravity picture, though derived from a distinct framework. Stefan Gielan and Lucia Menendez-Pidal worked within a framework called unimodular gravity, a reformulation of general relativity in which the determinant of the metric tensor is fixed to a constant value, effectively decoupling the cosmological constant from the trace of the energy-momentum tensor. When they applied the principles of quantum mechanics to this framework, specifically using an approach called unitarity, the requirement that the quantum mechanical evolution of a system preserves the total probability of all possible outcomes, they found that the singularity inside a black hole is replaced by a region of large quantum fluctuations in which the concepts of smooth space and time cease to apply in the classical sense. The key result of their paper is that beyond this quantum fluctuation region, on the other side of what the classical equations describe as the singularity, the space-time re-emerges as a white hole. Matter does not pile up at the singularity and disappear. It passes through the quantum fluctuation region and re-emerges. The paper further proposes something that the loop quantum gravity framework does not directly address. It suggests that the white hole phase could be where time re-begins. The idea depends on the role of dark energy, the mysterious component of the universe responsible for the accelerating expansion of space in the quantum description of time within the framework. Gielan and Menendez-Pidal propose that time, in this framework, is not an independent variable but is derived from the evolution of the quantum state of the universe in relation to dark energy. When the black hole transitions to the white hole through the quantum fluctuation region, the effective direction of time's derivation could re-emerge, meaning the white hole is not simply the black hole's continuation, but potentially a region where temporal evolution begins anew, in a form that the familiar classical description of time as a smoothly flowing universal parameter may not adequately capture. This proposal is described by its authors as a theoretical proposal, not an established result. It has not been independently confirmed. The unimodular gravity framework is not the standard formulation of general relativity, and its predictions differ in the regime of strong quantum effects. But it is a peer-reviewed result, published in one of the most prestigious journals in physics, and it represents exactly the kind of work that the frontier of theoretical physics looks like: imaginative, precise, technically rigorous, and making claims that are, in principle, testable, at least conceptually, even if the tests are extraordinarily difficult to perform in practice. The November 2025 research on what has been called the Einstein-Rosen caterpillar adds another layer to this picture, approaching the black hole-white hole connection from a completely different direction. The quantum informational structure of entangled black holes. The work, by a collaboration of researchers from the United States and Argentina, applied the theoretical framework of the ER equals EPR conjecture, itself a proposal by Juan Maldacena and Leonard Susskind in 2013 to investigate the internal geometry of a pair of quantum entangled black holes. The ER equals EPR conjecture is one of the most provocative ideas in contemporary theoretical physics. It proposes that two black holes connected by an Einstein-Rosen bridge, a wormhole, and two particles connected by quantum entanglement are not merely analogous situations. They are the same situation, described in different languages. Entanglement and wormholes, in this conjecture, are two different descriptions of a single underlying physical connection. ER stands for Einstein-Rosen, referring to the wormhole. EPR stands for Einstein-Podolsky-Rosen, referring to the 1935 paper in which Einstein, Podolsky, and Rosen first identified the paradoxical features of quantum entanglement. The conjecture is that these two phenomena, separated by decades of physics and by entirely different theoretical frameworks, are in fact identical. Every entangled pair of particles is connected by a wormhole operating at the quantum scale. Every wormhole is a manifestation of quantum entanglement between the regions it connects. The ER equals EPR conjecture has not been proven. It is a hypothesis, and a bold one. But it is a hypothesis that has attracted the attention of many of the leading theoretical physicists of the current era, precisely because it offers a potential bridge between the two greatest theories of physics, general relativity and quantum mechanics, and because it suggests a geometric interpretation of quantum entanglement that could be tested, at least in principle, through calculations in both frameworks. The November 2025 research used this conjecture to investigate what the interior of a wormhole connecting two entangled black holes actually looks like when the entanglement is not perfect and clean, but is scrambled when the quantum state connecting the two black holes is chaotic and complex, as it would be in any realistic physical scenario. The result was striking. The interior of the wormhole connecting the two entangled black holes is not the smooth, clean tunnel that the maximally extended Schwarzschild geometry describes. It is a long, complex, segmented structure, a lumpy, irregular passage whose internal geometry reflects the complexity and chaos of the quantum entanglement between the two black holes. The researchers called this structure the Einstein-Rosen caterpillar, named for the bridge and for the bumpy, segmented shape that the chaotic quantum state produces in the geometry of the wormhole interior. The complexity of the caterpillar, the number of segments, the degree of irregularity scales with the degree of quantum chaos in the entanglement between the two black holes. The more scrambled the quantum state, the more complex the interior geometry. This result has several implications that are directly relevant to the black hole-white hole story. First, it confirms that the connection between entangled black holes, the wormhole that the ER equals EPR conjecture says they share, is a real geometric structure in the sense that it has an interior that can be meaningfully described and analyzed. It is not merely a formal mathematical object, it has structure. Second, it shows that the wormhole interior is sensitive to the quantum state of the black holes at its endpoints. The geometry of the bridge between the black holes is not independent of the quantum mechanical description of the black holes themselves. It is determined by it. Third, and most suggestively, it demonstrates that the wormhole, even in its complex, caterpillar-like form, remains stable. It does not collapse under the influence of the quantum chaos. The firewall paradox, a proposal by Almhiri, Marolf, Polchinski, and Sully in 2012, suggesting that the interior of a black hole might be replaced by a wall of high-energy radiation that destroys any infalling observer, is not supported by the caterpillar geometry, which shows a connected, traversable, in principle, interior structure, consistent with the experiences of an infalling observer. Together, the loop quantum gravity black to white hole transition, the Sheffield unimodular quantum gravity result, and the Einstein-Rosen caterpillar research form a coherent, multi-pronged picture that is emerging from the frontier of theoretical physics. They come from different frameworks. They use different mathematical tools. They make different specific predictions, but they converge on the same broad conclusion: the singularity is not the end. The interior of a black hole connects to something. The connection is geometrically real, quantum mechanically real, and in principle, physically real. And what it connects to what sits on the other side of the quantum bounce or the quantum fluctuation region, what the caterpillar wormhole leads to in the fullest extension of the space-time is, by the internal logic of the mathematics, a white hole. Now, it is time to sit with what this means, not as a technical result, as a fact about the universe we inhabit, or rather, as a potential fact, a candidate truth that the mathematics is forcing on us with increasing insistence, even though confirmation remains out of reach. Here is the situation. Every black hole that has ever formed in the history of the universe is, according to the framework of loop quantum gravity, on a trajectory that ends with a quantum bounce and a re-emergence as a white hole. The 100 billion trillion black holes scattered through the observable cosmos. The supermassive black hole at the center of the Milky Way, Sagittarius A star, with its 4 million solar masses. The 6.5 billion solar mass monster at the center of Messier 87. Every stellar remnant, every collapsed core, every primordial black hole formed in the early universe. All of them in this picture are in the first moments of a process that ends with everything they have ever swallowed being returned to the universe. Nothing is lost. Everything that ever fell across an event horizon is preserved. The matter that formed the black hole, the stars that fell in, the gas that accreted over billions of years, the radiation that crossed the horizon. All of it, in the loop quantum gravity picture, survives the singularity because the singularity is replaced by the quantum bounce and re-emerges on the other side as the contents of a white hole. This is a resolution of the black hole information paradox, one of the most deeply troubling problems in theoretical physics. The information paradox arises because Hawking radiation, the thermal radiation emitted by a black hole as it evaporates, appears to be featureless, carrying no information about what fell into the black hole. If Hawking radiation is truly featureless, then when the black hole has fully evaporated, all of the information about its contents has been permanently lost, in violation of the fundamental quantum mechanical principle of unitarity, the principle that the quantum mechanical evolution of a closed system preserves all information. The loop quantum gravity picture offers a resolution. The information does not escape through the Hawking radiation. It survives through the quantum bounce and re-emerges from the white hole. The information is not lost. It is stored for an incomprehensible span of time in the quantum geometry of the bounce region, and then returned to the universe when the bounce completes and the white hole forms. This resolution has been discussed in the loop quantum gravity community by researchers including Rovelli, Vidotto, Haggard, and others, and it connects the black-to-white hole transition to one of the most productive problems in contemporary fundamental physics. The connection to the information paradox is not a proof that the loop quantum gravity picture is correct. It is a theoretical consistency check showing that the picture is compatible with quantum mechanical unitarity in a way that the classical picture of a singularity is not. The actual confirmation of this resolution would require experimental access to the quantum gravity regime, which is not currently possible with any existing or near-term future instrument. And here is where the philosophical weight of this story becomes unavoidable, where the mathematics and the physics and the observations all reach their limit, and what remains is the human confrontation with a universe that is deeper and stranger and more patient than our instruments can currently fathom. We began this story with the most extreme confirmed objects in the universe, black holes, photographed and measured and detected through the ripples they send through the fabric of space-time. We showed that the same equations that proved black holes real also contain a mirror image, a white hole written into the mathematics with equal inevitability. We showed that classical white holes are physically pathological, thermodynamically backwards, dynamically unstable, and without a formation mechanism. We showed that despite all of this, the equations refuse to retract the white hole from the geometry. And we showed that the most advanced theoretical physics of the current era, loop quantum gravity, unimodular quantum gravity, the ER equals EPR conjecture, and its caterpillar manifestation is converging on a picture in which the white hole is not a mathematical ghost, but a genuine future state of every black hole that exists. The universe may be perfectly symmetric after all. It may be honoring every prediction of its own equations. It is simply doing so on a schedule that makes every human timescale, every civilization, every star, every galaxy look like a momentary flicker at the opening credits of a story that has barely started. What does that mean? It means that the asymmetry we observe, the universe full of black holes and empty of white holes, is not a violation of the equations. It is a consequence of where we stand in time. We are observers who formed after the Big Bang, who developed science and physics and general relativity in the first 14 billion years of the universe's history. 14 billion years sounds long. Against the Hawking evaporation timescale of a stellar mass black hole, 10 to the 67th years, 14 billion years is not even the opening sentence. We are reading the first word of the first line of a document that fills a library the size of the observable universe, and we are describing that document as though we understand its plot. The universe may not be keeping secrets from us maliciously. It may simply be in the middle of a sentence. Every black hole that has ever formed is still in the inhalation phase of a breath that will not be exhaled for a span of time that has no name in any human language. We observe only the inhalation. We have never seen the exhalation. We call the inhalation black holes, and we call the exhalation white holes, and we marvel that the universe seems only to do the first. But perhaps the universe is doing both, as the equations demand, just sequentially, on a timeline so vast that the entire history of cosmic structure formation, from the Big Bang to the death of the last star, occupies a fraction of the interval between inhalation and exhalation. This is not a comfortable thought. It is not an inspiring one in the easy sense of the word. It is something stranger and more honest than either comfort or inspiration. It is the recognition that the universe is indifferent to our timescale. It operates according to rules that are perfectly symmetric, that honor both the black hole and the white hole, that preserve information and return matter to the cosmos, but that do so at intervals so vast that no observer who came into existence in the first 14 billion years of cosmic history has any hope of witnessing the completion of a single cycle. We are inside the process. We cannot step outside it. We cannot observe it from the beginning to the end. We can only read the equations and trust what they say, and sit with the recognition that the universe is keeping a promise we cannot yet see it keep. The white hole is not missing. It is waiting. Every black hole in the universe is a white hole in waiting. The singularity at the center of each one is not a wall but a threshold, a quantum transition region through which space-time passes from the collapsed state to the expanded state, from the trapping geometry to the anti-trapping geometry, from the darkness that swallows to the darkness that returns. The mathematics has been telling us this for over a century. General relativity contained the white hole from the moment Schwarzschild wrote down his solution in 1916. Kruskal and Sekeres made it visible in 1960. Loop quantum gravity made it physical, made it a prediction about actual events rather than a formal feature of an idealized geometry in the early 21st century. And the Sheffield paper of March 2025 and the Einstein-Rosen caterpillar of November 2025 are steps in the ongoing work of understanding exactly how the transition happens and what it produces. We do not know yet whether loop quantum gravity is the correct theory of quantum gravity. We do not know whether the unimodular gravity approach of Ghielen and Menendez-Peidel is right. We do not know whether the ER equals EPR conjecture is more than a beautiful guess. We do not know whether any gamma ray burst has ever been produced by a white hole, small bang. We do not know whether the Big Bang itself was a white hole event. These are open questions, genuine, unresolved, scientifically important open questions that the best minds in theoretical physics are actively working on, publishing on, disagreeing about, and slowly, carefully building the mathematical scaffolding to eventually answer. What we do know is this: the equations of general relativity, tested to extraordinary precision across more than a century of observation, contain both a black hole and a white hole in the same geometry. They always have. What we do know is that quantum gravity, whatever its correct formulation turns out to be, must replace the singularity with something that makes physical sense, and that the most mathematically mature candidates for quantum gravity predict a bounce, a transition, a continuation of spacetime through the singularity region into a white hole geometry. What we do know is that the absence of observed white holes is not evidence that the equations are wrong. It is evidence that the universe is patient in a way we are not equipped to intuitively appreciate. The boundary between what we can prove and what we can only calculate and theorize is where physics becomes most honest and most alive. We are at that boundary. The white hole is there in the equations, in the geometry, in the emerging predictions of quantum gravity. Whether it is also in the universe, in the sense of being a real physical object that will one day be observable is a question that belongs to the future. A future so far ahead of us that the universe we currently inhabit is, by comparison, essentially just beginning. Every black hole that has ever swallowed a star, collapsed a cloud of gas, consumed the light that fell past its horizon. Every one of those events is, in this picture, a deposit into an account that will not be withdrawn for intervals beyond reckoning. The universe is a place of extraordinary patience. The equations are symmetric, the physics is honest, and somewhere, at the deep future end of time, in a cosmos that has forgotten stars and galaxies and everything that existed in this brief luminous era, the first black holes will begin to exhale. We have the equations. The equations are waiting. And the universe, as always, will take exactly as long as it takes. Rest now. Stargazer, somewhere at the end of time, the universe is still exhaling